All right, so in the last video, I gave a basic introduction to the Galois group of a field extension. And I was talking a little bit about this extension, Q adjoin square root of 2 over Q. And we found examples of some automorphisms that belong to the Galois group of this extension. So this time I want to talk about one of the major facts from Galois theory. So this is really like a basic fact, but this is a fundamental one, which is that if you have an extension of fields, which is a Galois extension, okay, then the following is true. The size of the Galois group of L over K is equal to the degree of the extension. So some explanation is in order for what's kind of going on here. First of all, this word Galois refers to basically just a nice enough field extension. And I won't totally go into the details of everything that this means. But basically, this is a type of algebraic extension. So this is an extension where every element of this field L is algebraic over K. So it has a minimal polynomial over K. And then the other things that have to be true to be Galois is that the extension has to be normal and separable. So again, I won't get too much into details, but normal basically just means that so every polynomial over K that has at least one root in L factors completely in L. So this has to do with basically polynomials that have at least a single root have to have all of their roots in L. So that's basically what normal means. And then separable refers to what happens to algebraic elements of L. So basically, if an element of L is algebraic, you want its minimal polynomial over K to be a separable polynomial. And that just means that it doesn't have repeated roots. So this has to do with, are there irreducible polynomials that have repeated roots? Or does that not happen? And that never happens in Q, so you never have to worry about that. So extensions of Q are automatically separable extensions. But this is something that might show up with like more advanced examples. Okay, but so the point of this is that when you have at least extensions of Q, so this is an example of an extension that is in fact a Galois extension. And so this means that the size of the Galois group is equal to the degree of this extension. And what is the degree? So what's the degree of Q adjoin square root of 2 over Q? Well, it's the dimension of Q adjoin square root of 2 as a Q vector space. And so I was talking about that a little bit in the previous video, that what this field really is it's kind of like the span of two numbers. So it's just all of the rational linear combinations of 1 and square root of 2. And we can use that here because this set is actually a basis for Q adjoin square root of 2. And it has two elements. And so the degree in this case is equal to 2. But so what that means is that the size of the Galois group is equal to 2. So if you remember in the last video, we had these two maps. There was the identity, and then there was sigma naught, which were kind of like, this was kind of like conjugation. And these were both elements of G, the Galois group. And using this fact, which you obviously have to prove, and for time constraints I won't do that, but you know that the size of the Galois group in this case is equal to 2, and so that tells you that these are actually the only elements of the Galois group. So these two automorphisms that we found, these are the only elements of G. So G is literally just the set id, and then sigma naught, which was sigma naught was the conjugation map, like this. So that's it. And again, the Galois group is a group with respect to composition of these functions, these automorphisms. And up to isomorphism, there's only one group of order 2, which is Z mod 2Z. So that actually tells you that G is Z mod 2Z. Which is maybe obvious in this example, because if you think about what happens if you do sigma naught twice, the result of that is that you would flip the b squared of 2 to negative b squared of 2. And then if you kind of go, if you do that again, it flips back again. And so this does have a Z mod 2Z structure, right? There's an identity element, and then there's an element that if you do it twice, it's equal to the identity. So this is actually Z mod 2Z. And so kind of the point of what I wanted to do with this example is that with this particular extension, you can really narrow down what the automorphisms are. So you're like, okay, I have Q adjoint square root of 2. I want to know what all of the Q linear automorphisms are of this extension. And using facts from Galois theory, you can pretty much immediately say that like this is what the Galois group is. And you can also explicitly find the elements of the Galois group. Yeah, so that's a nice example. But maybe there are more complicated examples. And so now let's take a look at that. So if you look at this field extension, so this is immediately way more complicated. Previously, we were just adjoining square root of 2. Now we're adjoining square root of 2 and I. And so what this turns out to be, I'll kind of state this without proving it, but it's everything of this form. So you can kind of see that this is a 4-dimensional Q vector space. And yeah, it's basically all of the Q linear combinations of 4 things this time, right? So it's 1, we're adjoining square root of 2 and I, so those need to be in there. And then their product is also contained in this extension. So this is a 4-dimensional Q vector space. And using our previous fact, so basically this means that the degree of this extension is equal to 4. And so that tells you that the Galois group of Q adjoin these two numbers over Q, at the very least, the size of this is equal to 4. Okay, but so already we're running into problems because there are 2 groups of order 4. So, like the last example, we had Z mod 2Z. Well, now there's Z mod 4Z. But there's also the Klein 4 group. So these are the 2, up to isomorphism, these are the 2 groups of order 4. And so in this case, we need some way of narrowing down which one it could possibly be, right? And so this is a slightly more sophisticated example. And so this is kind of the game that you play in Galois theory. You generally want to know what the degree of a field extension is, which is this. And then once you know that, it tells you the size of the Galois group. And you can use other theorems and properties to narrow down which of the groups it could possibly be. So yeah, this is a slightly more advanced example, and I will continue it in the next video.